All right, well, we are ready to get started. It's really nice to see so many faces. I'm really excited for this talk, so I'm glad to see a mostly full room. For those of you who don't know me, my name's Scott Newbold. I'm a member of the biology department here at the college. And along with other folks in the life science department, we, through this lecture series, the Museum of Discovery Science Lecture Series, we bring a variety of scientists on campus to try to share their knowledge with us here. And sometimes that's regional, sometimes it's local. And so we're going to get a nice taste of a local topic with Wyoming geology tonight. Before we start, the last speaker in the Science Museum Lecture Series this semester is on December 4th, a Wednesday night. And the title is The Ice Age Legacy of Western Fishes, How the Beaver Can Turn Back the Clock on Climate Change. So that's a PhD candidate from UW, Niall Clancy, December 4th. All right, so my pleasure to introduce tonight's speaker. How many of us have traveled across Wyoming's vast landscapes and wondered how those landscapes came to be? Tonight, James will help answer some of these questions using a bottom-up approach, starting from the geology under our feet. James has been a geologist with the Wyoming State Geological Survey since 2019. He holds a BS in Earth Sciences from Montana State and an MS in Geology from Utah State. He specializes in geologic hazards, geologic mapping, and geomorphology, and is especially fond of any project that takes him into the field to study geologically active landscapes. His work at the WSGS includes mapping surficial geology and geomorphology for 7.5 and 30 by 60 quadrangles, inventorying and analyzing landslides, and studying quaternary active faults. Please welcome James Mauch.
Awesome. Thanks for the introduction, Scott, and thanks for inviting me up here. I'm excited to present in front of this audience. Thank you all for coming out this evening and for folks who are tuning in on Zoom. So the talk I'm going to give tonight is really a 30,000 foot flyover view of all things Wyoming geology. I named it From Granitoids to Glaciers. I was trying to come up with an alliteration, but suffice it to say, we're gonna cover a lot of ground. And I have two goals for the presentation. The first is to hopefully equip all of you with some tools and background information that you can apply when you're out and about in our wide open landscapes and you wonder how they came to be. So whether you're a longtime geology enthusiast, maybe you took a class or two back in high school or college, or if this is the first time you've ever had some instruction on geology, hopefully there's a tidbit or takeaway that you'll get from this presentation. And then the second goal is to convey to you guys and hopefully leave you with an appreciation for just how lucky we are in Wyoming with the great diversity of geologic features that we have. This state really is a great place to observe geology in action. And before I launch into it, I want to give just a little bit of background on the state agency that I work for, the Wyoming State Geological Survey. We're one of the smaller state agencies, so there might be folks who aren't familiar with us. The Wyoming State Geological Survey, it's a non-regulatory state agency. We were established back in 1933. And you can see our mission here. It's kind of a two-pronged mission to promote the beneficial and responsible development of our state's energy and mineral resources, as well as to understand and inform the public about geologic hazards. So basically, our charge is we're responsible with studying Wyoming's geology and disseminating that information for the benefit of Wyoming citizens. Our office is on the University of Wyoming campus, right behind this famous T-Rex statue. So if you happen to find yourself in Laramie on a weekday, come stop by. I'd love to see you. And this is our website right here, where you can find all of our publications to download for free, some interactive maps, and a lot of other tools and resources. And so my niche with the State Geological Survey, my kind of specialty is geomorphology and geologic hazards. I also do a lot of geologic mapping. So my kind of purview falls in this second prong of our mission. And before I forget, there's some postcards and some informational pamphlets up front. So after the presentation, feel free to come grab some, as many as you like. We have a lot of these. So in keeping with our theme of this kind of 30,000 foot flyover, I like to start with this slide, which is a satellite image of our roughly rectangular state, and use this opportunity to emphasize that somebody like me, a geologist, is really lucky to get to work in Wyoming. And that's for two main reasons. One, which I already alluded to, is just the wide swath, the great variety of geologic features and processes that are present within our state's boundaries, spanning all the way from old rocks, deep time, up to modern day active geology that we can observe. And then the second reason I'm lucky to work in Wyoming is that the geology is front and center. It's almost impossible to ignore it when you're driving across the state. It's all visible to us, which is a lot different than folks who have the unfortunate reality of working, say, in the eastern US or in the Pacific Northwest, where you have to look very closely at things like road cuts, because most of the geology is obscured either by vegetation or urban development. We're lucky in Wyoming in that that's not the case, and we can see it all front and center. So a little overview. This talk is going to have two parts. The first part, I'm going to try to get us all up to speed on some of the fundamental concepts of the science of geology. And then in the second part, I'm going to step through Wyoming's geologic history and give some examples and vignettes from various parts of the state. So let's launch into the first part here. And one of the fundamental challenges of geology is that the forces and processes that shape our planet occur on such vast timescales that an individual scientist or multiple generations of scientists, or in some cases, all of human history, cannot firsthand witness these forces and processes at work. So we have to turn to things that we can observe, and that's primarily the rock record in the modern landscape. But of course, the rock record is not perfect. It's fragmented. As we go farther back in time in the rock record, it gets more difficult to tease out what happened. We have things like overprinting, where more recent processes have kind of obscured what happened farther back in time. And another factor is that the rock record really in any one location is incomplete. There is missing time in the rock record. And this photo I'm showing here is a photo by Mark Fisher from the awesome website geowyo.com. And this is showing a road cut just to the west of Cody, between Cody and Buffalo Bill Reservoir. And I've annotated it. You can see that there's a really old rock at the bottom of this outcrop, 2.6 billion years old. And there's a much younger rock at the top of the outcrop that's 520 million years old. And between these two rock layers is over 2 billion years of missing time. So that's a little bit problematic for us as geologists if we want to get a comprehensive picture of kind of a chronological events. So what this means is we have to go to different locations on the landscape where we might be able to find the rocks that are missing in any one location. And I'll return to this concept later, but the idea of missing time here is encapsulated in what geologists call an unconformity. The rock on top is much, much younger than the rock below. One of the ways that we address these fundamental challenges is through this concept of uniformitarianism. That term is a mouthful, but it can be summed up by kind of this catchy statement here, which is that the present is the key to the past. And what this means is that as a geologist, I can go and observe a landscape or a rock outcrop, such as if I go to the west of Lander here and observe, this is called the Nugget Sandstone. And I can make some observations that this rock here is composed of sand grains that are primarily quartz, and they're all pretty much the same grain size. And that those sand grains are held together by a cement, and that they're arranged in such a way that they create these kind of big brushstroke kind of texture that we call cross-bedding on a meter or 2 meter scale. And I can take those observations and I can compare them with something I can see on the modern landscape. For instance, if I go to the Sahara Desert, I've never been there, but if I were to go there, I would see similar qualities that these sand grains are primarily quartz. They're all about the same size, and they're arranged in such a way that they have these big sweeping crossbeds. Then that allows me to make some inferences about what the environment was like when the sediment forming this rock here on the right was deposited. And that's kind of how we calibrate ourselves in geology. It's really kind of the fundamental way that we make inferences about the past. And if it weren't for this concept of uniformitarianism, I would submit we'd kind of be reduced to some wild guesses. Another fundamental concept, which I've already alluded to, is just the vastness of geologic time. This is kind of a conceptual diagram of how geologists subdivide geologic time into different periods. And so on the left of the diagram, this is back at the formation of the Earth, old, and that gets younger to the right, and this is the present day here. And all these colored boxes are different subdivisions of geologic time. And I won't go into all these other kind of clear boxes here that are pointing out major events, but I will provide the analogy that perhaps some folks have heard of before, illustrating the vastness of all this time. If we compress the whole swath of geologic time into 1 year, the oldest rocks we find on Earth would have formed around February 13th. The first life would have appeared somewhere around March 27th. The dinosaurs would have become extinct around December 19th, so getting pretty close to New Year's. You think of that as a long time ago, but in the span of geologic time, fairly recently. And then, of course, humans would have first appeared only 22 minutes before midnight on December 31st. So we're very recent arrivals on the scene. Another fundamental concept is that of the rock cycle, which is kind of this conceptual idea for how various Earth materials form and are morphed and shaped into different Earth materials, and how that material kind of gets recycled. And so new rocks, novel material, all start out as molten material or magma beneath the Earth's surface and the subsurface. That magma, if it cools and solidifies, it becomes a rock known as an igneous rock. If that igneous rock is exposed at the Earth's surface, it will weather and erode into sediment, which is unconsolidated material that's not yet a rock. But if that sediment is buried and compacted and cemented, it can become a sedimentary rock. And then if that sedimentary rock is subjected to some heat and pressure, maybe it's partially buried in a mountain building setting, it'll undergo physical and chemical changes, making it a metamorphic rock. And then metamorphic rocks can be melted again to become magma. And of course, there are other pathways through the middle of the diagram. An igneous rock can melt again to magma or be subject to heat and pressure to become a metamorphic rock. Sedimentary rocks can weather back to sediment, etc. And this leads us to our three main rock types, terms that might be familiar to some people. And these three rock types are sort of the fundamental way that we classify rocks. And so as a geologist, when I pick up a hand sample, when I'm out and about and I pick up a rock and I wonder how it came to be, the first question I ask myself is just basically, what type of rock is it? Is it an igneous, a metamorphic, or a sedimentary rock? And so igneous rocks, as I mentioned in the previous slide, these are ones that cool directly from a melt. These are the new rocks that come to the Earth's surface. And we classify igneous rocks as to whether that magma cools below ground in the subsurface, in which case we call them intrusive igneous rocks, or whether that magma makes it to the surface of the Earth and then cools, in which case we call them extrusive igneous rocks. An example of an extrusive igneous rock would be a basalt, and an example of an intrusive igneous rock would be a granite, which is what's shown here from a rock just to the east of Laramie. And then our second type of rocks are metamorphic rocks. Again, these ones are produced due to kind of direct physical and chemical changes when an existing rock is subject to heat and pressure and sometimes shear. And we classify these according to their foliation, which just means how well the mineral grains are aligned, how well those long axes are aligned, what minerals make up that rock, and then the grade. So in other words, how hot was that heat and how much pressure did that rock undergo? Examples of metamorphic rocks are gneiss, schist, quartzite. This is a photo of a gneiss in the Teton Range. And then finally, we have sedimentary rocks, which form from the consolidation of sediment or minerals that may precipitate from a solution. Importantly, sedimentary rocks are deposited in flat-lying layers, and that allows geologists to sort of read sedimentary rocks often like a book. If you go deeper down into deeper layers, you're going back in time. And our subdivisions of sedimentary rocks there's sort of three classes. We have clastic sedimentary rocks, which are formed by the mechanical breakdown of other rocks. This is kind of the classic sedimentary rock you might think of as a sandstone, as shown in this picture. We also have chemical sedimentary rocks, which can precipitate directly from a solution. An example of that would be a limestone. And then organic sedimentary rocks, which are derived from the breakdown of organic material. An example of that would be a coal. And importantly, sedimentary rocks are the type of rocks where we preserve fossils, which are very important when we're trying to understand what happened in the geologic past. And then a final housekeeping note on this slide, I'm going to refer throughout the presentation to crystalline basement rocks. And when I say that, I just simply am taking igneous and metamorphic rocks kind of together as one. If we look at the Earth's internal structure, we see that it is stratified and segregated into some discrete layers. So at the very center of the Earth, we have the core, composed of the solid inner core and the liquid outer core. And the core is where the Earth's internal heat is generated. And this heat comes from both the breakdown of radioactive elements, as well as some leftover heat that's kind of residual from the formation of the planet. Above the core, in this diagram, kind of the orange and yellow colors, this is the mantle. The mantle is actually mostly solid, but over geologic time, it behaves a little bit more like a viscous fluid, so kind of a thick, syrupy fluid. And importantly, the mantle kind of transmits the heat that is generated in the core up towards the surface. And so there are large convection currents that occur in the mantle. And then way at the top, the kind of the outer eggshell, if you will, of the planet, what we're standing on now is known as the crust. And there are two types of crust. There's oceanic crust, which underlies most of the oceans, displayed on this diagram here on the left. And the oceanic crust is a lot thinner. It's very dense. And then we have also continental crust, which underlies the continents. That's a little bit thicker, more buoyant than the oceanic crust. And I've already thrown a lot of terms, so apologies in advance. Geologists love their terms, and to complicate things further, but it's important for the next slide. We also have these terms of lithosphere and asthenosphere. And the lithosphere is basically the crust and the very uppermost mantle taken together. And these behave rigidly, importantly. And then the asthenosphere is part of the upper mantle that is most fluid and where these convection currents are most active. And those concepts become important when we're talking about plate tectonics, which is the geologic theory through which pretty much all large-scale geologic processes are understood. It's the lens through which we understand a good bit of geology. And the theory of plate tectonics states that the lithosphere, so that rigid body at the surface of the Earth, is composed of discrete plates that move relative to each other and essentially float on top of this fluid asthenosphere. And it's the movement of these tectonic plates, and the plates are kind of shown in this map here. It's the movement of those plates relative to each other that drives large-scale geologic processes, particularly those that occur at plate boundaries, so places where two plates intersect. And those locations are where a lot of the action happens, things like mountain building, volcanism, and earthquakes. And of course, there's a few different ways these plates can move relative to each other. They can be coming together, in which we call that a convergent boundary. So if you have two continental plates coming together, both of those plates will kind of bow up and thicken, like if you kind of compress a rug. An example of a continent-on-continent collision would be the Himalayas, the highest mountain range on Earth. If oceanic crust and continental crust come together, that oceanic crust is, again, a lot denser, so it's kind of dive under that more buoyant continental crust in what we call a subduction zone. example of a subduction zone would be along the west coast of South America, where the Andes Mountains are rising up. And you often get volcanism in those settings, and what's kind of displayed in this part of the diagram. Then you can also have plates kind of moving apart. We call that a divergent boundary. And often when you get that, you have novel mantle-derived material kind of upwelling. A lot of these divergent boundaries occur in the middle of the ocean, and we call them mid-ocean spreading ridges. And then finally, you can have two plates on sort of the same plane that are moving parallel with each other, but just in opposite directions. We call those transform plate boundaries. These often occur as little steps or jogs in mid-ocean ridges, as is shown in this part of the diagram. And then the example in a continental setting would be the San Andreas Fault in California. Okay, this is my last slide for sort of concepts, and I threw it in because this is something I nerd out about. I'm a geomorphologist. I'm interested in landforms and processes that shape the Earth's surface. And it turns out that the processes that shape the Earth's surface really can be boiled down to endogenic processes, which are those that build up topography, and exogenic processes, those that wear it away. And the shape of the Earth's surface is a product of that kind of ever-present battle. And so these endogenic processes that build up topography are primarily driven by the Earth's internal heat. So again, coming from the core, transmitted through the mantle up to the crust. Examples would be mountain building and volcanism. And if you look at the Himalayas, that's a place where we are seeing endogenic processes in action. And then these exogenic processes that wear down topography are primarily driven by energy from the sun. So in other words, weather patterns, processes that happen in the atmosphere and weather and erode rocks away. And examples of that would be river incision, landsliding, and glaciation. And it turns out that river incision in continental settings really is the most important of these exogenic processes. Rivers are great sort of transmitters of signals of erosion between the oceans and the high mountain ranges. And they're also giant conveyor belts that export a bunch of sediment. As you can maybe see in this photo, this is a still from a video taken of the Lamar River in Yellowstone National Park in June of 2022 when we had those big floods. And to me, this is like exogenic processes in one frame. There's a lot of wearing away of topography going on in that photo. Okay, let's move on to part two, where I'm going to walk through some of Wyoming's geologic history. A little bit of housekeeping on this slide. In the subsequent slides, you'll see a little map in the bottom left corner of Wyoming with a white star. That white star just refers to the location I'm talking about in that particular slide, or perhaps the location of where the photo is taken from. And then here's our geologic time scale again at the bottom, with old being to the left, young being to the right, and these different boxes referring to different subdivisions of geologic time. And then the arrows here are referring to sort of the time period that I'm addressing in that slide. So just a little bit of like orientation for space and time. So it turns out the oldest rocks in Wyoming are those that belong to the Wyoming province, which is this sort of ancient microcontinent that was one of several microcontinents that came and accreted together or were sutured together to form an ancient continent known as Laurentia. And the Wyoming province, as the name would suggest, underlies what is now much of Wyoming, which is I've shown here by this white box, with the exception of the kind of the far southeast part of our state, which was underlined by a younger province known as the Yavapai province. And the zone where these two provinces came together and sutured together is known by the Cheyenne Belt. And that's important both geologically and economically today. It hosts a lot of unique mineral systems that a lot of my coworkers at the State Geological Survey are currently studying. And I like to think of these ancient provinces accreted together. There was a paper in the 80s that referred to these as the United Plates of America, and I always thought that's kind of catchy. But it turns out United Plates of America is actually a show on the Food Network. So if you want to learn something about the Wyoming province, just Google United Plates of America, geology, and you'll get there. One of the places we can see these old rocks from the Wyoming province is the Medicine Bow Mountains. This is a photo of a metamorphic rock, a gneiss that's about 2.7 billion years old. And you can see these Wyoming province rocks in the core of a lot of our mountain ranges, including places like the Wind Rivers and the Tetons. A little bit younger, but still pretty old rocks are another suite of igneous rocks known as the Sherman granite. And the Sherman granite was formed as part of a kind of a broader period of magmatism throughout North America around 1.4 billion years ago. And the Sherman granite is primarily exposed today between Laramie, Wheatland, and Cheyenne, kind of in the Laramie Mountains there, and extends a little bit into Colorado as well. And one of the best places to see the Sherman granite is up at Vidavoo Recreation Area, which is where this photo is taken from, which is just to the east of Laramie. And if you're ever up at Vidavoo, take a good close look at these rocks. It's really cool. There are some very large mineral grains, specifically some of the feldspars can be up to 4 to 5 centimeters long, which indicates that this rock cooled very, very slowly in the subsurface. There was a lot of time for those mineral crystals to grow. Then we have a period where there's a bunch of rocks that are just missing in Wyoming. There's missing time. This comes back to our idea of an unconformity. In fact, we call it the Great Unconformity. Almost 1 billion years that are missing from the rock record in Wyoming. And it's believed that during this time, there was widespread erosion that was occurring on that ancient continent Laurentia. And because of that erosion, all of those rocks were removed from what is now Wyoming. But that doesn't mean these rocks don't exist anywhere. We can go to neighboring states to see them, places like Glacier National Park in Montana, which is where this photo is of, the Uinta Mountains in Utah, as well as the Grand Canyon in Arizona, all have rocks from this time. But again, this brings us back to that concept of an unconformity. And I'll return to this picture to emphasize that while across Wyoming, this kind of gap in the rock record is somewhere around 1 billion years. At any one location, it might be way more than 1 billion years, such as this road cut just to the west of Cody, where that gap is over 2 billion years. Then we enter a long period of quiescence, multiple hundreds of millions of years, where there was a kind of a broad, shallow sea off to the west of Wyoming. And this part of North America, where Wyoming now sits, was kind of slowly subsiding. And that seaway was moving eastward, coming in. I call that, this is, again, I'm just giving little monikers that help me remember these things, but I call this all quiet on the Western Front. And this period of subsidence and sedimentation, it kind of kicked off with this particular rock unit that you see in this photo. This is the Flathead Sandstone. And the Flathead Sandstone was deposited in a terrestrial setting, so essentially rivers. And as that seaway progressed in from the west, in the rock record, we see evidence for changing environments of deposition. So as we go up in the sedimentary rock record from the Flathead Sandstone, we start to see shales and carbonate rocks such as limestones and dolostones that indicate more of a shallow ocean setting. And so this photo here, this is from the Wind River Canyon. This is showing the Madison limestone, which was deposited in a warm, shallow sea. If you drive through Wind River Canyon, it's really great. You cut through most of this sedimentary section that records this period of quiescence, all the way from the basement rocks, and you go up through the Great Unconformity, and you cut through this sedimentary section. This period of quiescence was interrupted around 300 million years ago by the uplift of the ancestral Rocky Mountains. And as the name would suggest, these are not today's Rocky Mountains as we know them, but a mountain range that existed in kind of some of the same locations. So this map on the right, this is a paleogeographic reconstruction by Blakey and Rainey. You can see this seaway off to the west that I referred to in the previous slide. And then you can see in this area of Colorado and New Mexico and extending into southern Wyoming, there's an uplifted mountain range. And the result of this is that if we go to southern Wyoming, a lot of these sedimentary units, such as the Madison limestone or the Flathead sandstone that were deposited early on in this period, are actually gone. They're eroded away And that was because as these mountains uplifted, that sediment that was deposited, like the Flathead sandstone and the Madison limestone, was kind of eroded away all the way down to the basement rocks. So if you go to a place like the Laramie Mountains, just outside of Laramie, you will have much younger sedimentary rocks that rest directly on the basement rocks. We return to a period of quiescence at the beginning of the Mesozoic era. And one of the sedimentary units that was deposited during this time is one of our most distinctive rock units, known as the Chugwater group. You will have noticed the Chugwater if you've seen the brilliant, bright, rusty red color of rocks that are often on the flanks of mountain ranges in Wyoming. One of the best places to see the Chugwater is to go to the aptly named Red Canyon, which is between South Pass and Lander. That's where this photo is taken from. You can also see it around here if you're heading up into the Bighorns from Dayton. Right before you start up the S curves and switchbacks, you're going to cut through red rock of the Chugwater group. And the Chugwater was deposited in sort of a quiet coastal setting. Another important episode in our state's geologic history is the period in the late Mesozoic, when there was a large interior seaway that connected the Arctic Ocean essentially to the Gulf of Mexico. And it ran right through Wyoming. And this seaway, the level of that seaway, or the position of the shoreline, fluctuated east and west over time. So this is another paleogeographic map by Blakey and Rainey. And this particular time stamp, around 84 million years ago, shows that western shoreline of the seaway about along Wyoming's western boundary. And importantly, along these shoreline settings, there were extensive swamps. And there was a bunch of organic matter that accumulated in those swamps and became peat. And that peat was buried and compressed to become coal as it was buried. And the coal that was deposited during this time is mined in southwest Wyoming and outside of places like Rock Springs and Kemmer. You can see sedimentary rocks that were deposited in the western interior seaway through many of Wyoming's basins. This is a view of the Cody Shale outside of Casper. A view like this is familiar to folks anybody who's traveled through Wyoming. It creates a lot of our kind of distinctive wide open spaces and badland topography. Okay, that period of quiescence for multiple hundreds of millions of years was finally interrupted and came to an end in a big way, starting about 120 million years ago, with two mountain building events that were sort of back to back, and they overlapped in time a little bit. And this is my demarcation for, if you can time travel back to Wyoming before these mountain building events, it would have looked nothing like it does today. These mountain building events are when Wyoming starts to look like the landscape that we know today. And that first mountain building event is known as the severe orogeny, and orogeny just means mountain building event. And the severe orogeny occurred between about 120 and 50 million years ago. And it was that this event was such that the mountain building kind of started off to the west of Wyoming and what is now Utah and Idaho, and through time kind of progressed eastward into the state. And the severe orogeny is characterized by thin-skinned deformation or thin-skinned faulting. And what this means is that the faults that uplifted these mountains were restricted and relegated only to the relatively thin sedimentary cover that overlied the crystalline basement rock. So in this kind of cartoon cross-section here of the severe orogeny, you have faults that don't penetrate into the underlying basement rock, which is kind of shown in this brown color. And what this looked like is essentially big sheets of sedimentary rock being shoved and thrust over each other in sort of an easterly direction through time. And we can see the products of the severe orogeny if we go to Wyoming's westernmost mountain ranges. So the Salt River Range, the Wyoming Range. This photo here is from the Wyoming Range, and it's looking north. And this peak here is composed of a sedimentary unit that is actually older than the rocks to the right here that are under it. And the reason these rocks are here is because they were kind of thrust up and over the younger rocks to the right. So again, that thrust faulting occurring kind of from east or from west to east direction. Our second mountain building event, hot on the tails of the severe orogeny, is known as the Laramide orogeny, which occurred in Wyoming between about 70 and 35 million years ago. And Wyoming is really ground zero for the Laramide orogeny. A lot of the classic Laramide mountain ranges that geologists think of are here in our state. Mountain ranges like the Bighorns, the Wind Rivers, the Laramie Mountains, the Medicine Bows, the Gros Ventres, even the Black Hills were all uplifted during the Laramide orogeny. And unlike the severe, the Laramide orogeny is characterized by thick-skinned deformation or thick-skinned faulting, which means that the faults that uplifted these mountain ranges did in fact penetrate and involve the crystalline basement rock. And that's what's shown on the right side of this cartoon cross-section here, with this mountain range being uplifted and involving kind of the brown color of the crystalline basement rock. And it turns out that the amount of vertical uplift that occurred along these Laramide faults is to me like an astounding amount. For instance, if you go and you stand on the highest peak in Wyoming, Gannett Peak, above 13,000 feet, if you want to find those same rocks that you're standing on just 20 miles to the west beneath the town of Pinedale, you'd have to go 32,000 feet below sea level to find those same rocks in the bottom of the Green River Basin. So that amount of vertical uplift between Gannett Peak and the bottom of the Green River Basin is something like 45,000 feet. It's really a stunning amount of vertical uplift that occurred in Laramide time. And a natural question is one, what caused these mountain building events? And two, why did the deformation style kind of switch from thin-skinned to thick-skinned faulting? And to answer the first question, both of these mountain ranges, both of these mountain building events occurred because off to the west coast of North America, along the western boundary of the North American plate, there was a subducting plate of oceanic crust that was, again, diving below that more buoyant North American plate. And that oceanic plate is known as the Farallon plate. And it was that subduction of those two plates coming together that caused the compressive forces that are responsible for both of these mountain building events. The answer to the second question as to why that deformation style switched is a little bit more complicated and is not fully resolved by geologists. It's something that a lot of geologists are still working on, and is an area of active research. But one of the ideas is that the angle of this subducting plate sort of shallowed through time, such that the Farallon plate eventually was kind of scraping along the bottom of the North American plate, if you will. This is kind of been the classic interpretation, and it also is sort of the classic interpretation invoked to explain another interesting phenomenon of the Laramide orogeny, which has always puzzled geologists, which is, why did this mountain building event occur so far inland from the plate boundary? If you consider mountains like the Black Hills, essentially in South Dakota, that's a long way from where this plate boundary would have been. And it's a lot different from other settings that we see on the Earth today, such as along the western coast of South America, where the Nazca plate is subducting beneath the South American plate, and the Andes just rise straight up from the coast, essentially. So this idea of this flat slab subduction has been one of the hypotheses that geologists have about why the Laramide orogeny occurred so far inland into Wyoming. And again, that idea that shallow angle of the subducting plate would have caused those compressive forces to be sort of transmitted so far to the east. But certainly that's not the only hypothesis and still an active period of research. At the tail end of the Laramide orogeny, we had a large kind of broad scale period of magmatism throughout Western North America. And one of the products of this magmatism, which occurred in a period known as the Eocene, is one of our more famous landmarks, Devil's Tower, as you can see in the photo. And the geologic interpretation of Devil's Tower is that This rock is an intrusive igneous rock, so it represents some molten magma that was intruded into the crust, but that it probably never reached the surface of the Earth. It cooled below the Earth's surface, and that the rocks that it intruded into were subsequently kind of eroded away to leave this monolith standing. This is the preferred interpretation, over thinking of Devil's Tower as like a feeder conduit to a volcano, because of two reasons. One is that if this was kind of the feeder vent to a volcano, we should see more volcanic deposits in this part of the state, which we don't. And the second reason has to do with looking at the distinctive texture of Devil's Tower. You see the kind of the vertical striations along the side of the tower, which are so characteristic. And these are formed by columnar jointing. And columnar jointing occurs when an igneous rock cools. It sort of compresses and shrinks a little bit and forms these beautiful hexagonal columns. And it turns out that the grain of these columns is roughly perpendicular to the cooling surface. So when we look at Devil's Tower, we see that the grain of these columns is roughly vertical, which means that the cooling surface was roughly flat, somewhere above the monolith. If this was a kind of shallow volcanic vent, we would expect a little bit more kind of flaring out of these columnar joints, if indeed there was, you can imagine a mound or a conical shaped cone above Devil's Tower. So that's kind of the interpretation there. We can go to other places in the state to see the effects of this Eocene magmatism, such as the Absaroka Range. Most of the rocks you see in the Absarokas are extrusive igneous rocks. So these cooled at the surface of the Earth, primarily in the form of ashfall, lava flows, and some volcanic debris flows, otherwise known as lahars. But all of this kind of magmatism at both Devil's Tower and in the Absarokas was occurring at about the same time. Another cool product of this time period can be found in southwestern Wyoming. And this is when the Laramide and Sevier mountain ranges were first starting to erode. And so you can imagine as these young mountain ranges are just kind of starting to erode away, the river systems that are draining these mountain ranges are just kind of getting established. They're in their infancy. And some of these river systems hadn't yet broken out and established a course all the way to the oceans, meaning that they were internally draining into some of these internally draining lakes. That would have been much like the Great Salt Lake is in Utah today. And there were several of these internally draining lakes in southwest Wyoming and extending into Utah and Colorado. And if you can imagine, just like the Great Salt Lake, these interior lakes were very salty and briny. And as specifically, especially during kind of low stands, when that water was low, you had a lot of minerals precipitating out of these waters, out of solutions, which leads to a lot of the kind of the economic activity. It turns out in the Green River area, one of the minerals that was precipitating out of these lake systems is trona, which is a sodium carbonate mineral. Trona has a lot of industrial uses, including in the manufacture of glass. And there are trona mines just to the west of Green River, and those owe their existence to these internally draining lakes. Another factor that owes its existence to these internally draining lakes is the just remarkable preservation of fossils in rock units such as the Green River Formation in southwest Wyoming, places like Fossil Butte National Monument. Again, these were pretty calm water settings, and so any organism that died in that water column and floated down to the bottom was buried in sediment, sort of in a quiet manner, was not disturbed. And that today yields the outstanding fossil assemblage that we see in the Green River Formation, including our state fossil Knighthand. Okay, as the period of mountain building that I've been talking about kind of wound down, we had sort of a counter reaction, I like to call it. So in the Sevier and Laramide, as I mentioned, the crust was sort of being compressed because that Farallon plate was subducting. After the end of that subduction, all of that compressed and over thickened crust no longer had anything actively compressing it to kind of hold it up. And so you get this period of kind of relaxation of the crust, which has led to generally crustal extension in the western US. Basically the crust being pulled apart. And this is seen most prominently in other places in the West, such as Nevada, and is responsible for what's called the Basin and Range Province. So if you drive across Nevada on I-80, you'll go over a mountain range and down into a basin and up over a mountain range. And all of these mountain ranges are bound by fault systems that are down dropping the adjoining basins. And that's what's shown in this diagram here. And so the point is that this crustal extension has made its way into westernmost Wyoming and is responsible for our our sort of pattern of alternating valleys and mountain ranges that we see in western Wyoming, including places like Star Valley and the Salt River Range, Jackson Hole and the Teton Range. And the faulting that has led to the down dropping of these basins relative to the uplift of the mountain ranges is still active today. This is why western Wyoming is the most seismically active part of our state. It's where we have the most earthquakes. And another way that we can tell that this faulting is still relatively active is we can go to the landscape and see places where earthquakes in the geologically recent past have actually ruptured the ground surface. We call these fault scarps. This is an example of a fault scarp in this photo right along the base of the Teton Range above String Lake. And the arrows point to the fault scarp, which is kind of this over-steepened shaded area here right at the base of the mountain front. And it turns out these fault scarps are all over the place if you look for them in western Wyoming. And people like me get excited about them because they are evidence of recent, very geologically recent fault activity. And new technologies such as light detection and ranging, remote sensing allow us to pick these things out, and they are all over the place. I'd be remiss if I didn't include a slide on Yellowstone for a talk about Wyoming geology. Compared to everything I've talked about up to this point, the volcanic and hydrothermal activity in Yellowstone is a very recent arrival on scene. So the Yellowstone Volcanic Plateau in northwest Wyoming here is the product of 3 large caldera-forming eruptions that have occurred in the last 2.1 million years, as well as a lot of basalt and rhyolite flows that sort of occurred between those large eruptions. And the reason that we have the volcanic and hydrothermal activity that we do at Yellowstone is that there is an upwelling of hot mantle material associated with a hot spot that is right now directly beneath northwest Wyoming. And that's leading to high heat flow and thin crust in this part of the state. And it turns out that we have evidence for this plume or hot spot of material upwelling from the mantle. We have evidence of its effect on the landscape all the way back, stringing back about 16 million years, starting in kind of southeast Oregon and working its way up the Snake River Plain, getting progressively younger to about the present day where Yellowstone is. And this is not because the hot spot has migrated this direction, but instead the hot spot is stationary and the North American plate has been migrating to the southwest. So the Snake River Plain, you can kind of think of it as the wake of the trace of that hotspot as the North American plate has moved to the southwest. The very last kind of major episode of Wyoming geology that we can see widespread on the landscape is the legacy of dozens of glaciations that have covered our mountain ranges in the past 2 million years or so in an epoch known as the Pleistocene. And at least in the last 2 of these glaciations, which are really the only 2 that we have abundant evidence on the landscape for, in those last 2 glaciations, Wyoming was well south of the major ice sheets that covered much of Canada and extended into the Great Plains and Midwest of the lower 48 as well. Wyoming was well south of that, but our highest mountain ranges, including places like the Bighorns, the Wind River Range, hosted large glacial systems. And the largest of which occurred in the northwest part of our state. It's called the Yellowstone Ice Cap. This would have been a mass of ice that covered all of the Yellowstone Plateau, the Absaroka Range, the Tetons, the Beartooths in Montana, sort of all as one contiguous mass of ice. And a lot of these mountain glaciers, they of course started in the high terrain and then kind of flowed outward down slope. A lot of them actually flowed out of valleys and spilled onto our more arid basins at lower elevations. And we can see this very clearly along both flanks of the Wind River Range. This photo is taken of Fremont Lake, which is just to the east of Pinedale, and looking this direction towards the Wind River Range. And Fremont Lake is a sort of a deep trough that was scoured out by a glacier that came out of the winds, flowed through Pine Creek, and kind of spilled onto the floor of the Green River Basin, scoured out a bunch of this sediment, and also deposited a bunch of the sediment that it was carrying kind of off to the sides. It sort of pushed or shoved a lot of that rock that it had quarried out of the Wind River Range off to the side. And that's why you see big boulders like this kind of sitting on these ridge-like landforms that we call lateral moraines. And so the ice that was coming out of these mountain ranges would have started to recede somewhere around 15,000 years ago. And say by 12,000 years ago, these glaciers had receded enough up valley that they were just kind of in the more upper Cirque Basin headwater areas. And so that sort of, that takes us to the end of our geologic story. Just kind of one summary slide. I like to convey to folks who are interested in geology that the science relies on our power of observation across scales. So that includes at the scale of a single rock that you may pick up and try to identify and to figure out how that rock came to be. We observe things like the mineral composition. What are the minerals that make up that rock? And the texture, how those minerals or grains are put together. And by observing those two kind of simple qualities, we can say a lot about what type of rock it is and how it might have formed. And this power of observation can be applied to the large scale too. When we're looking at an entire landscape, we can observe processes that are acting on that landscape and make comparisons with what we see on the modern landscape versus what we might see in the rock record, allowing us to make inferences about what occurred back in the geologic past. Again, this is the idea of uniformitarianism. The present is the key to the past. And then if I were to sum up Wyoming's geologic history in 5 bullet points, these would be them. So we have the oldest rocks in Wyoming, the root of North America, this ancient continent, Laurentia, the United Plates of America, if you will. Then we have this period of where we don't see any rocks in the rock record in Wyoming that represent this period, missing time, our great unconformity. Then we have the long period of quiescence, multiple hundreds of millions of years where it was all quiet on the Western front, and Western North America was kind of subsiding and a tropical seaway was coming in. Then we have our 2 back-to-back mountain building events, the Sevier and Laramide orogenies, which are the start of the topography that we recognize in Wyoming today. And then the recent landscape shapers that are still active, we can still witness these today, such as river incision, glaciation, and active faulting. And that's all I have. Thanks for your attention, appreciate it. And don't forget handouts up front if you like. Happy to take questions too.
Is that period of extension still thought to be related to the rollback of the Farallon Plate?
Yeah, that's another idea. I mean, so the Farallon Plate after the Laramide time, one of the ideas is that you get the subduction of sort of the western boundary of that Farallon Plate, and as that occurs, yeah, that slab, instead of being such at a flat angle, begins to roll back a little bit, which puts less compressive stress on in the interior west of North America. And that's one of the ideas for basin range extension as well. Yep.
Okay.
Yeah.
Couple of questions. First, all of this missing rock, just to think of how that was all transported is just mind-boggling. But is that what went all to fill in the western interior seaway and form the middle of the U.S. A and all of that?
Yeah, well, that's where a lot of it goes. Yeah, if you go out to eastern Wyoming, some of our younger rock units that are exposed at the surface there, those are all eroded off of those laramide mountain ranges, transported in east flowing rivers, and that sediment is still stored, if you will, on the North American craton in those younger geologic units. Some made it out to the oceans, but a lot of it is still stored as sedimentary rocks. Yep.
And the other thing was when you had the two orogenies there, Laramie and Sevier, there was part of your slide that showed a suction, and you didn't mention it, and I couldn't. There we are, increasing suction in the top there underneath the Proterozoic lithosphere.
Yeah, I mean, I won't be able to do total justice to this idea, but one of the ideas, again, you get sort of these plates of these lithospheric plates are subducting into the asthenosphere. And again, the asthenosphere is where you have these convection currents circulating around. So one of the ideas is that as you have these kind of convection currents circulating around, that might have something to do with like pulling this Farallon plate up to the surface. That again, there's probably more nuanced explanations than I can give to their wording of suction, but that's what I assume they kind of mean there.
And the other thing in the origin of the basin and range, there's cooling of this Farallon plate and shrinking because of the cooling. Does that have anything to do with that construction of basin and range?
The cooling of the Farallon plate itself, or
Yes.
yeah, but potentially, I think most of it. I think at the heart, and both with slab rollback and any other mechanisms that are invoked, sort of the heart of them is that the fact that the Farallon plate, we sort of reached the western edge of the Farallon plate, and that was subducted, and that gave rise to a different plate boundary off to the west of North America now. And that plate boundary is now the San Andreas Fault, essentially, in California. Yeah.
I've always been curious on how the Wind River Canyon was formed.
Yeah. Oh, that's a great question. I took out some slides, but it's one of my favorite sort of sub periods of Wyoming geology. So Wind River Canyon, there's a lot of canyons, it turns out, in Wyoming that are like the Wind River Canyon, places where rivers, our modern day rivers, sort of cut through mountain ranges perpendicularly. And you kind of look at that and you're like, why did the river establish that course? There's a much better way it could have gone by going around that mountain range. And the answer is that the Wind River through Wind River Canyon and a lot of other places in Wyoming, such as where the North Platte cuts through the Seminole Mountains or the Laramie River cuts through the Laramie Range, these are what we call superimposed rivers. So as all of that sediment was being eroded off of the Laramide mountain ranges, it was filling these basins. And again, just like I showed in this slide here, a lot of these were internally draining basins. There wasn't external drainage established. So essentially all the sediment just piled up in the basins, and it piled up to such an extent that many of the mountain ranges were really just buried up to their necks. Some of these mountain ranges were completely buried by that sediment. And so then you have the rivers kind of establishing their courses on this sediment that had buried all of the mountain ranges. And then starting around 10 million years ago, the whole Western US started uplifting. And right at that time, all these rivers started downcutting back into that sediment that had previously buried the mountain ranges. So if you imagine, these rivers had kind of established their course independently, and they started downcutting, and eventually they reached that hard rock, such as what forms the Owl Creek Mountains where the Wind River cuts through. But by that time, those rivers, they had established their courses. They weren't going to change their courses. They just kept incising lower and lower. And that's why you get these rivers that cross our mountain ranges perpendicularly, such as Wind River and Wind River Canyon. Yeah, superimposed rivers. That's what that's called. Yep. Yeah.
Many papers show the craton boundary on the east as including the Black Hills or we believe it's buried there,
Uh-huh.
headed in that direction. But then more later papers are showing the craton boundary as just out here on the east side of the Bighorns. Do we have any idea which is more likely to be?
Oh, boy, I'm sorry. I'm not the person to answer that question. Yeah. No, I don't know. I'd have to, there's some of my coworkers could give you a better answer than I could. Yeah.
Is there anything you can tell us specifically about the geology of the Bighorns?
Yeah, so the bighorns are, I didn't use them as an example much in this presentation, but they are like the Wind River Range, a classic laramide uplift. So the faults that uplift the bighorns cut into the crystalline basement rock. And you have some really beautiful exposures of those faults right along the east side of the bighorns here. If you go up Highway 16 from Buffalo up into the range, there's one of the most beautiful road cuts in the whole state is right along there. And you see a lot of the vertical beds of the I think it's the Paleozoic section that you see the beautiful flat irons. And these rocks are upturned because of thrust faulting, leading to the uplift of the bighorns. And then more recently, the bighorns, like the other high mountain ranges in Wyoming, were glaciated, and there's extensive evidence of glacial deposits and scoured out landforms in the bighorns that you would see in
There's evidence
textbooks.
out here, at the mountain base of ancient peneplain.
Yeah.
And if you dig into that peneplain, in any quarry I've ever seen out there, all of the rocks are rounded and water,
Yeah.
there. So is that a result of the glaciation? How did all those rocks get there? At the base of the
Yeah.
mountain?
That's a great question. And it would depend on the age of that peneplain or pediment or Piedmont.
Right.
But the short answer is that all of that material did come from the bighorns. It's the product of, again, that laramide mountain range eroding away. If those are gravels that were deposited in the most recent geologic period in the Pleistocene, they likely were deposited by glacial outwash. But it turns out there's a lot of these Piedmont features in Wyoming that are much older than the most recent period of glaciation. And so it's tougher to sort of connect the dots to glaciation. And all you can say really is that these were transported by rivers that were, again, acting as large conveyor belts for sediment that was eroded from the mountain range, and that was sort of trundled along, and that's why all of those cobbles are rounded, and then deposited next to the mountain front. And if on a broad scale, you sort of follow those features out into the basins, you should see a basinward sort of fining of that sediment, such
It
as
does happen that way.
yeah, close to the mountain front, it's going to be the bigger cobbles and boulders, and as you get farther out into the basin, it's going to be finer grains.
But there's no angular at all out there. It's all waterworn.
Yeah, and you're exactly right. Yeah, when you see these rounded cobbles or rounded gravels, it tells you that those were transported some distance, most likely by rivers, and that's how they were kind of abraded and made into a rounded shape. Yep.
Just an observation that a property in Bighorn where we live is all granite that we see there, and all the rest of it, I guess it wasn't tough enough to persist.
Yeah. That's a great observation. Yeah, and you see that in river deposits and also glacial deposits. Same along the flank of the Wind River Range. You look at all of these boulders here; they're all granite, and it's really due to two reasons. One, the younger sedimentary rock is a lot softer, so it'll erode away and won't be preserved as large boulders. And then the other reason, at least in this photo, these rocks were all kind of quarried from the core, the high mountain peaks of the Wind Rivers, and then transported out. Similarly, in the Bighorns, a lot of the glacial deposits you see along the flank, it's the same thing. The material that these glaciers were eroding came from the highest peaks. So naturally, it's going to be the basement rocks that you see. So kind of a combination, but yeah, it's a great observation.
Can you comment on the structural geology of the Bighorns in terms of, like, there's three sections. There's the excuse me, I have to think about it a second. There's the eastward verging thrust fault on the north, and then the central, it's westward verging. And then, I think this is right.
And then eastward verging on the south again.
Right.
I believe so. Yeah, unfortunately, I can't provide much more information than that either without looking at the map a
The
little
cool thing is
closer.
you can tell by just looking at the dip slopes.
Yeah,
Oh,
exactly.
that's the trailing edge of the fault. It
Yeah.
went whatever, west east.
Yeah,
But it's so much fun to point out because the trees will tell you and the dip slope.
yeah.
Right? Yeah.
Yeah, that's a great observation. Yeah, definitely. We rely a lot on, I've made the comment that most Wyoming geology we can see because there's no vegetation. Where there is vegetation, it tells us something usually. And the comment about the different sort of ways in which these thrust faults verge is also an apt one when we're talking about these laramide mountain ranges, because most of these laramide uplifts were asymmetric. So there's one side that the fault really moved on and uplifted, and then on the other side there's usually some kind of back thrusts or other faults, but generally the rock is less disturbed on that backside. And so if you go to again a place like the Wind Rivers, on the east side of the Wind Rivers at Lander and Dubois, you see the very nice kind of slanting just dip slopes of sedimentary rock, where it's different on the west side where we have all that displacement, and you get similar things up here in the Bighorns.
Just so people might not know, but if you're driving to Casper and you look at the mountains, the best way to see it is right at Crazy Woman.
Yeah.
And there's really steep dip,
Yeah.
you know, the flat irons, and then you've got this beautiful dip slope, right? Boom, like that, the dips. And I just love looking at it every time.
Yeah. Yeah, we're lucky. Yeah, we see those views, driving on the interstate and stuff. Yeah, it's
Can
pretty
you tell
cool.
us anything about the rare earth element discovery up in this area?
Oh boy, I hate to say this again. Like there are people in my office who could tell you everything about it. It's not really it's not the area that I work in. Come chat with me afterwards. I'll give you some contact info. Yep. Yeah.
So if this area, like just out of town where it had the coal mining history, probably from the Eocene, Paleocene, lakes and swamps contributing to the good coal quality in the Powder River Basin. Then where were the sources of the natural gas and the oil that Wyoming has an abundance of? Were those related to the Western Interior and the Sundance Seaway? And did both of those intrusions create coal, or did they create gas or oil, or where does the oil and the gas come from?
Yeah, that's a great question. So we have multiple formations throughout the state that are source rocks for oil and gas, including rocks that would have been deposited in the Western Interior Seaway during the Cretaceous and in the Sundance Seaway. Also during older, back further in geologic history during the Paleozoic, kind of all quiet on the Western Front. Basically, all of these are derived from organic material that gets buried, and whether it becomes oil shale or gas bearing or oil bearing, just depends on how deep it was buried and what temperature window and pressure window it was subjected to. And so we get these from multiple formations.
Just depending on heat and pressure and
Yeah.
the local setting then?
Yep.
Okay, thank you.
Yep.
All right, well, let's thank James again very much.